So here's an example. If you kind of tie back with the unit that we just got done, Kinetics, or not just got done, several weeks ago. How do you complete a kinetic question that contains a fast equilibrium as one of its elementary steps? So if you look below, this should look very familiar. You've got your mechanisms here, slow, fast, and we know that our slow step is our rate determining step. But what happens when one of those elementary steps has what's called a fast equilibrium? Okay, so here we're just going to walk through the problem. It says determine the overall reaction, okay, and the rate law that corresponds to the mechanism given below. Okay, so the overall reaction is pretty easy. That's where you just add up your befores and afters, okay? It's the rate law step that might be a little more difficult if a fast equilibrium is present. Okay, so if we add all these together, let's do the overall first. Okay, remember anything that exists on the same, on the reactant side and the product side, we can cancel out. Okay, and so I would either write all of the reactants down and then cancel them out, or you can just kind of go through and notice that ABC and ABC, okay, those can cancel out. Okay, A is good, B is good, C is good, D is good, it looks like AD and AD, BC is good, E is good, and AD. So if we were to write the overall, it would be A plus B plus C plus D plus E yields BC plus ADE. So this is that's AD, our overall reaction. So that's good. Okay, so how do we write the rate law now? Okay, because we know that this one has intermediates, okay, and they are present in our mechanism, we want to first look at our slow step, because that is our rate determining step. Okay, so we can write rate equals, now I'm going to say step 1, step 2, step 3. When we write the constants for these, for the rate law, K1, K2, K3, just so we can get this. So this one would be rate K2, because it's step 2, and we only write the reactants. So A, B, C yields D. Not yields D, but just times D. Now, this is something that's a little new. Okay, because this is an intermediate, intermediates cannot be in our rate laws. Okay, so to get rid of our intermediate in our rate law that's written from the slow step, we need to look for a step before the slow step that contains the intermediate, which in this case we know in step 1 there's a fast equilibrium. Now, this is the tricky part that I want to kind of expand on. So I'm going to kind of zoom in here and rewrite this fast equilibrium step and kind of show you a way that we can manipulate this. So A plus B plus C, it's an equilibrium step, yields A, B, C. So let's define the forward reaction as K1. But because this is equilibrium, we can also define a reverse reaction. And what we're going to do here is express that as K to the negative 1. And so we can write a rate law in that reverse direction if needed. Now, we have our rate. We're trying to get rid of the ABC. We want to find a way to substitute ABC. So we want to solve for that. Now, because of the last section with equilibrium, we know that the rate of the forward reaction equals the rate of the reverse. And so we can use our fast equilibrium step and write two rate laws, okay, that are set equal to each other. First one is K1 if we're going in the forward direction, and that's equal to the reverse, which is K to the negative 1, A, B, C. So now if we solve for A, B, C, okay, at equilibrium, we can rearrange that and get A, ABC equals K1, A, B, C divided by K to the negative 1. And we can substitute this portion of ABC back into our original rate law. Okay, and so what that gives me is rate equals K2. ABC is going to be K1, A, B, C over K to the negative 1 times the concentration of D. And what you can do here, okay, is pull together all of these constants. Probably should have done a different pen color so that kind of pops. You can pull out all of these constants and write your final rate as K2, K1 over K to the negative 1 times A, B, C, and D. Okay, if there was another intermediate in our rate law, you would do the same thing to substitute it out. But this would be our final answer. So not much too different. Okay, so in our notes, we're going to stop here for right now. Relationship between delta G and the equilibrium constant is, we will look at those in Unit 7, in addition to solubility, equilibrium, common ion effect, but I wanted you to have a chance just to kind of get caught up on those types of questions. In my email, I will tell you which problems too.